Good afternoon. Dwayne Walliser here. It's my pleasure to introduce today's Center for Climate Sciences seminar. David Legler, David, that's funny. He knows the gist of that joke. But David Lavers from ECMWF. I'll give a short introduction. I didn't prepare very well for that, but I can vouch for David, how smart he is and what a nice guy is. I've known him for several years. He got his PhD at University of Birmingham, and that's not Alabama in this case. And then he did postdocs at University of Reading, Iowa, and at Scripps, and that's where I met him. So about 5 years ago, I spent a little bit extra time at Scripps over multiple weeks, and that's when David got hired by Marty Ralph as a postdoc. And so we had a lot of interaction over atmospheric rivers and lots of other stuff. And I learned how nice and smart he is about what he does. And then after that postdoc, he went to work for ECMWF. And he had a little bit of a short stint before that at ECMWF as well. So his area of expertise really is like hydrology, hydroclimate, weather forecasting. And today he works kind of half and half in two different things. One is diagnostics related to forecasts, especially with Marty's AR Recon program, you know, the one that goes out and does dropsondes in atmospheric rivers over the winters, and he looks at that data and looks at diagnostics from the forecast system. And then he also works half of his time with the Copernicus program. And so we're fortunate to have him here today because he's came over to attend Marty's biannual International Atmospheric River Conference, which this year is in San Diego, which is next week, but he wanted to come visit us for a day. And so thanks for coming, and have at it. Welcome.
Thank you, Dwayne. Well, Dwayne, thank you for those kind words. It's a pleasure to be here again. It's a little longer than 5 years. I can't believe it was 10 years. We're aging well, I think. Or I hope we are. Pleasure to be here, Dwayne. Thank you for the invite to come up to see you. Lovely to see you all in the audience. And
so I was told by our technical crew that if you don't see an image on the screen, if you're remote, that looks right and it looks like it might need some help, chat to Wingsy, and she might have a way to improve things. There's some key shift thing that you can do that might improve your settings.
Questions to the recording.
Oh, yeah.
Questions should go through the mic.
Yeah, so, and we'll welcome questions along the way or at the end, but we want to use the mic for questions here, like this, or if you're online, we'll entertain questions later too.
Yeah, very happy just to keep it moving. Any questions, anytime.
And I think Wingsy monitors the chat along the way, so.
But the point is anyone in the room asking a question has to go to the mic.
Yeah, or come up
No
here,
problem.
yeah. Thanks.
No problem at all.
The last three introductions I made in this room, I forgot to mention that. Use the mic. So I mentioned it 3 times just to make up for it. Use the mic, folks, when you ask a question.
Sounds good. I don't know if they heard that online. Do you want me to? Never mind. Anyway. Okay. Lovely to see you all. Lovely to be here. Thank you for being in the room on a Friday afternoon as well, and online. So I'm going to give a little seminar today on 2 different topics. So as Dwayne introduced, I'm working partly on climate monitoring, partly on forecast diagnostics, largely in today's talk using AR Recon, Atmospheric River Reconnaissance observations, and we'll talk about those later on. But first of all, I'm going to talk to you about the climate monitoring side, and then we'll move on. So it's a talk of 2 halves. But before I get to that point, I'd just like to introduce what the European Weather Centre actually is. European Centre for Medium Range Weather Forecasts, ECMWF. You could think of it colloquially as the weather centre of the weather centres. So there are multiple weather services across Europe. So if I can ask you to look at the right-hand diagram here, the dark blue countries, these are the member states, of which there are 23. The light blue ones, these are the cooperating states, which there are another 12. So there are 35 currently member or cooperating member states. Mostly known, I would say, still for the integrated forecasting system, the IFS, the ECMWF model, European model, as you might hear on certain news channels over here. So that's currently at 9 kilometers globally in the 51 member forecast, but we can come on to that. I'm happy to answer any questions on that. And we've just achieved or gone past the 10th anniversary of the Copernicus program. So the European Centre for what I'm going to talk about today. They implement the Climate Change Service, C3S, but they also implement the Copernicus Atmospheric Monitoring Service, CAMS, and implement part of the Copernicus Emergency Management Service, CEMS. So there are 3 particular services at the center. And I just basically said this, but the main points or main topics of today's talk, I'd like to take you through some of the main climate monitoring activities, which are under the C3S banner. So they're the annual summary, European State of the Climate Report, which we're just getting over now. That was out in April, and then the monthly bulletins, and we'll go through those. But we're not just doing regular monitoring, we're also trying to do research, evaluations in the background to try and improve what we can say about the Era 5 product in particular, which I'll come on to for climate monitoring activities. So I'd like to take you through a few specific things on evaluating Era 5 precipitation, and then one thing which we've just put together, and it's just under consideration. This is the extreme event ratio, and we'll come on to that. And then the last part, the last half, hopefully it'll be a half by the time we get there, will be AR Recon. So it's the Atmospheric River Reconnaissance, really very relevant for all of you folks here in terms of where this campaign is over the Northeast Pacific, but it's also growing across the whole of the Pacific, but then potentially going further around the world as well. So just very briefly, and then we will move away from these word-heavy slides, I promise you. The Era 5 reanalysis, what is this? This is the 5th generation reanalysis product produced by ECMWF. So this is a data set which is a merging of observations with a short-range forecast, so you have this consistent product using one particular cycle of the IFS, the Integrated Forecasting System. This is, for those who want to know, is cycle 41R2. Currently, as I say, it's Era 5, roughly 30 kilometers globally. They're working on Era 6, which will be the new product that comes out starting next year. And as I said there, so it combines model data with observations. You produce this global data set. You've probably heard it before, but I'll say it again. Maps without gaps is something that they talk about. This is basically a reanalysis. There are hourly estimates of the atmosphere, ocean waves, and the land surface, and we use it really heavily for the climate monitoring side. We do use other products as well, so we have an uncertainty estimate, or at least a little bit of confidence in what we're showing, but this is used largely for our monitoring activities. So I mentioned at the beginning different products we have that go out, different publications. The first one that comes out in the first week of the year, this is the annual global summary. I'm just showing you a map here. This is from 2023. I only show it just to show the state of the climate, obviously, for last year, and the warmth. I'll just pull out a couple of particular regions. If I can just ask you to look at the map on the left-hand side, last year you'll be aware that we've gone through an El Nino phase, a warming in the northeast equatorial Pacific, pardon me, I'm jumping ahead to AR Recon, in the eastern Pacific, and you can see that just here, this red region here, which I've got there marked on the screen. If we go to Europe, it's been much warmer than normal, other than across Scandinavia, so they've had a really cold period, which is now ended, but that's something we have been looking into. And then in terms of closer to home for you here, it was relatively cold compared to normal, compared to the 1991 to 2020 period over the western United States there. So that's the global map. If we look at it as a time series, so this is in Era 5. They do match the observed data sets well, these particular temperature anomalies. So this is the anomaly compared to the latest reference period, 1991 to 2020, and it's just showing how warm the last year has actually been, partly to do with El Nino, not all to do with it. So with the warming SST, sea surface temperatures, this has a knock-on effect onto the atmosphere. And you can see that red line. So if I just show you the whole plot, the blue lines, these go back to the 1940s, 50s, 60s, and as we get towards the more modern era, you see the more red colors, the warm colors that come out, and 2023 has broken the record completely. As you can see, that bold red line right at the top of the graph here. And I'll show you an updated plot of that in a few slides' time. So that comes out in the first week of the year. The second major product, which takes quite a bit of time during the first quarter, this is the European State of the Climate Report. Similar in scope, it's a little bit more similar in scope to the BAM's State of the Climate Report. we're mostly focused on Europe. There is a global section in there. There's a huge amount of information. Just on the right-hand side, if I can just ask you to focus on these different front covers. We've obviously evolved as time has gone on, which is natural and what you need to do. The first one was in 2017, so in the top left of that right-hand figure, as you can see here, then 2018, 19. I came into it in the 2020 report, so I've been in it for the last 4 years. And our latest one, the latest evolution has been to really employ data visualization techniques. And this one here on the bottom, so the bottom right of the screen as you're looking at it, this is all modeled on actual data. So our data visualizer who's just joined us, these are the last 4 decades, I believe, so 80s, 90s, 2000 or noughties, 2010s, and then the latest period. And all of these petals that you see on the flowers, these are the average annual temperature anomaly. So you can see the bluer colors back in the 1980s. As we go towards the present day, we get the red colors, and we're trying to picture the state of the climate in terms of impacts and impacts on vegetation in particular. So it's been an effort to try and visualize the data, try and capture people in a more natural way, if you like. And then this map on the left, you've basically seen that before. So in the interest of time, this is just focused on Europe. I will move on. A lot of my work, Dwayne did mention, is on hydroclimate, hydroclimatology, precipitation, rainfall extremes. One of the topics or aspects of this latest climate report, so as C3S, the Copernicus Climate Change Service, we're focused mostly on Europe, smaller domain of Europe. But we've now combined with the WMO, so the World Meteorological Organization for Europe. They have their own climate reports, state of the climate reports for each WMO region. And the WMO region 6, which is the European domain, we've now come together so that we don't have 2 different products coming out. So we have a C3S and the WMO. And what I'm showing you here, on the left-hand side, this is the anomalies for the precipitation across European land. So this is a much smaller European continent. Whereas on the right-hand side, this is for the broader WMO Region 6 domain. You do see a similar pattern between the two. You're using slightly different data sets. In the left-hand side, we're using ERA 5 and an in-situ product called EOBS, which comes from KNMI in the Netherlands, the Weather Service, National Weather Service of the Netherlands. On the right-hand side, this is ERA 5 and the GPCC, the Global Precipitation Climatology Center, I believe, and that's at DWD. So you see a similar pattern in both of them. 2023 was it the 3rd or 4th wettest across Europe, and similar across the broader domain as well. So just to show that it's evolving, we've gone from smaller Europe, bigger Europe, data visualization. It's growing all the time. The last one, the monthly bulletins. There are also ad hoc web articles as well, but the monthly bulletins, the next one will be released in the second week of July. So I'll be back to write that back then. So the one at the start of July will be for June. So this is our latest one. This was for May 2024, just showing the different products. I won't go into all the details of it, but we'll describe what's happening, for example, across Europe, across the world, and then put it into, obviously, the context of what's gone before. So that was May. June will be coming soon. And the latest one, which I promised I would come back to, so I showed you this for 2023. This is the most up-to-date plot that we have. So this is from June 2023 to May 2024. So this is the last 12-month period. And this is showing you that most of the months during that period, so 11 of the 12 months, they have been above, in our estimate from ERA 5, they've been above the 1.5 degree temperature threshold or anomaly given in the Paris Climate Agreement. So we've reached a bit of a point here. Whether or not it's going to go back down, it does certainly look like it at the end, but this is the first period where we've seen such a long extended time of Dwayne.
You said something about the Paris Agreement. Is that reference period a well-defined thing used within the context of the Paris Agreement? So that
yeah, so the 1850 to 1900, that's the reference period in the Paris Agreement. What we've done here is take the anomaly for all of these months with respect to 1991 to 2020. And then there's an offset added from the estimate of the 1850 to 1900 period onto that latest reference period. And the anomaly added is, I think it's 0.88 degrees Celsius. That's the estimate. That's the best estimate we have that we use is 0.88, and then plus the anomaly, which gives us the value there. And I can come back to that later on, Dwayne, and confirm that with you. Yeah, great question.
Has this been published in a way that sort of says, hey, we're over 1.5 now? We've exceeded it, rather than, has it getting that kind of attention yet?
So it has in the monthly bulletins. I believe the Secretary General of the WMO has made similar statements as well. I think there was one statement made last year about global boiling. You might have heard that one, but that was I think that was last year, not following this recent activity. It is going down a little bit, which could be to do with El Niño's weakening. La Niña is starting, but I should highlight as well, which I didn't do before, it's not all El Niño. There are other aspects around the world. The North Atlantic has been much warmer than normal, amongst other places. So the El Niño is part of it, but it's not all that's driving this particular feature that we're seeing. No, thank you, Dwayne. So I'd like to move. So that there is some of the climate monitoring we're doing. Sorry for the self-citation here, but I'd just like to show you that we're doing also evaluations in the background, as I said earlier on. One of them, obviously these maps without gaps that I've spoken about, we have data everywhere, but how good are these data around the world? So that's one thing I'm going to get onto in the first topic, which you can see there, this first publication, and then just show you, obviously we would expect the reanalysis to improve as we go from ERA 5 to ERA 6. We have another 8 years of physical model improvements. You have a higher resolution. It's planned to be 14 kilometers compared to 30. But is there anything we can do more immediately to improve our estimate of precipitation? And we'll come on to that one there as well. So this particular study, what we wanted to do, we were always a little bit reticent about showing stuff in the tropics or showing rainfall in the tropics, not stuff, because we know that the model struggles more in the tropics because of the convection, which we don't get as well, partly with the model grid, partly with the land-sea interface. So if we just think of the maritime continent region to the east of this map here. So what we tried to do is to pull together an observed precipitation data set. These are all from station data, so SINOP data across the world. We've merged different times. So these are 24-hour precipitation totals in terms of reporting. So we pulled together ones reporting at 00. And of course, that doesn't cover the whole world. The bulk of it, yes, but we then had to pull out ones reporting at 01, 03, 4, and 5. I'll explain that because you might think I've made a mistake. 06 and 12. And when you pull them all together, you nearly get 6,000 stations, which is a pretty large sample to have a look at what's going on in ERA 5. Now you might ask, why is that 0405? And I will tell you, because it was quite an intriguing little diagnostic. This area is in Australia. And what I found is that roughly 180 days we're reporting at 04, roughly 180 days at 05. I thought, well, this is a little bit odd. And it was basically due to stations reporting at local time, not UTC. So you ended up with these big dropouts, and I ended up with no data there. I thought, well, I can't. I know the data exists. And talking to a colleague about this, he informed me that it was quite regular, and I'm not sure about now, for these station observations to be taken by a station postmaster or postmistress. So basically the US Postal Service, our Royal Mail equivalent. It's wonderful that we've got the data, but you've got to be a bit careful about how you process it. So that's why it's 0405. It's reported at local time. So you have to merge them together to get the data set. Anyway, just thought it might be of interest. So the first thing we looked at, we used 20 years worth of data, just showing you the mid-season months, January in the top left, April top right, July bottom left, October bottom right, and this is the bias. So this is ERA 5 minus the observation, and then we've taken the mean. So we're just looking at the mean difference or the bias between them. And there's obviously a lot going on here. I'm just going to pull out 3 different things for the purpose of today's talk, because if I went through all of those, we'd be here a long time, as you might say. First big thing to look at, if I can just ask you to look at the top 2 panels, comes out in the bottom 2 as well, but the top 2 in particular. What you see here is a broad area of light blue colors. So basically this is telling us that ERA 5 or the IFS has a slight wet bias. So it's wetter than what we see in the observation. And in terms of, we've got the winter in the top left, boreal winter, northern hemisphere spring in the top right. This is partly to do with this drizzle problem that we have. So you end up with too much light precipitation on dry days, which gives us this wet bias that you see, and that's captured very nicely with the blues right the way across. As I promised, just 2 other areas I'll highlight. One, I think, for you in the US, which might be of interest. Looking at this plot, so we're now looking at the bottom left for the people online. So the bottom left plot, and in particular, if we just focus on the United States and Canada, there's almost a difference in bias from Canada to the United States. It almost follows the border, to be honest. And you end up with a dry bias across the continental United States and a wetter bias in Canada. And some of the diagnostics that we did on this, it seems to show that this could be related to irrigation in the US. And in particular, so ERA 5 doesn't have any soil moisture observations going into it. But what we found, especially across the central United States, where you have a lot of the crops that are grown, there were soil moisture increments in ERA 5, which was adding moisture, but it just never got to enough, and it ended up drying out. It just didn't have enough there. So basically what I'm saying is that by not having enough moisture, there wasn't enough recycling, which means you end up with not enough rainfall produced in ERA 5, and it gives you the dry bias that we see. So that's the hypothesis, that it was to do with soil moisture or lack of. And the other area of interest as well, which then goes out, of course, into the hurricanes that form off of Africa. So if we can just ask you to have a look at Western Africa, you see we get quite a big problem here with the convective activity, the mesoconvective systems that you see there. So those are 2 particular issues in terms of the bias. And I should say, we're looking at this because we're thinking, what can we say in terms of climate monitoring? Can we be sure of what we're seeing? The next one to have a look at here, this is the standard deviation of the error. So the mean error, that's looking at the bias. We're now looking at the random error. So you've taken out the mean by looking at the standard deviation. And what you find is that it moves. It moves with time, it moves with season. And if we just, for the purposes of this talk, we just focus on the top left, so January, you can see the darker colors, or the violet, the magenta colors, across the maritime continent, towards Madagascar and into South America. This is telling you that we're not getting the ICTZ, not Z, zone right. And what you then see is that as it drifts or it moves north from January down to July, you end up seeing that region is shifting north. So the biggest errors are with the tropical convection zone. That's basically what we see in this. And the other thing to highlight is that the tropics obviously have the biggest problems, the biggest errors. If you go to the extratropics, we do have problems, and they grow in the summer season when there's more convection, but it never reaches the higher levels that we see in the tropics. Extreme events. This is one thing, obviously it's important for all of us in society. This is just to show you how does ERA 5 capture extreme events. It does have issues. I would say it like this: it captures the patterns well. It's not going to get the magnitude right. So wherever you have the highest totals, it doesn't do it particularly well, but it does get the patterns correct. Some particular problems, I'm just going to go through them here just very briefly. Top left, tropical cyclones. This was in Australia, where number one, it's not going to get all the convection. Number two, it doesn't model as well as possible the land-sea interface, so you end up with issues there. Top right, this was an atmospheric river event. I think it was Storm Desmond, as it says up in the top panel, so the top right. And in particular, just one point, because the orography is too low within the model, you get too much overshoot, which you see in the top right panel and the bottom left. And probably the bottom left storm, Alex, this sums it up quite perfectly. The orography is too low, it's too flat, so you end up with too much moisture going over the top of, this is the European Alps. So if you look to the south of the Alps, we end up with, on average, too much rainfall. If you go to the north of the Alps, there's too much rainfall, there's too little on the south, there's too much on the north. So you end up with this spillover, which might be slightly corrected as you go towards ERA 6. That bottom one there, I'm going to come back to possibly on the next slide if I've remembered. This was a severe flooding event in Germany that led to more than 200 fatalities, and we'll come back to that in a moment. Next slide, I think, after this one. But what I wanted to just show you here, everything that we've done so far has been on ERA 5 precipitation, but from the short-range forecasts. So one thing that I mentioned at the beginning is, yes, we have a new reanalysis coming along, ERA 6, which will give you improved physical processes, it will be a higher resolution, but is there anything that we can do before that, and even within ERA 6, to provide users with a better estimate of precipitation for climate monitoring and other purposes? So what this is doing, so let me just repeat. So ERA 5 generally uses the short-range forecast. So when I say that, we're talking about 0 to 12 hours in the future. So that doesn't have any, it has observations that's gone into the system, but not into that forecast. What we can do is we can use the last trajectory, so the last run in the data assimilation system. And this last run that they have, this brings in observation. So that run should be more constrained by observations. And not to overload you on a Friday afternoon, because I would not want to do that, I just want to show you exactly the same stations that you saw in the earlier slides. What I'm showing you here is the relative difference. So we're looking at the error, this is the root mean square error of the ERA 5 traditional short-range forecast minus the observation. And then we're now we're doing that, and we're comparing it with the error that you get from using the 4D VAR, or the last trajectory from the data assimilation system. And to cut a long story short, if I just show you the top panel, so this is the relative percentage difference between those two runs. Wherever you see blue colors, this is for all days over a 20-year period, wherever you see blue colors, this suggests that the last trajectory of the data assimilation system gives you a better estimate of the precipitation. And that's at roughly 90% of the stations. So 87.5% of the stations have a smaller error, which is telling us that we can generally gain a better estimate of precipitation by using this particular precipitation estimate. There are issues, and I will just show you because I would want to give you all the information so I'm not just cherry picking here. If we look at Northern Hemisphere winter, so DJF, so the December, January, February days, we do see problems over Europe and over Canada. And this goes back to the comment I made earlier about the dry days being having an issue with a drizzle problem. So what we find is that the 4D VAR, the last data assimilation trajectory, you're adding in data, which then gives the system a little kick, which it responds by pushing out too much drizzle. So we do see problems as well. But generally, this is a very positive message. But let's move on to something which I hope will be of interest to climate monitoring activities, maybe just putting certain events into a context. So this is a latest piece of work. I promised I'd show you the storm over Germany. So I can just ask you to look at the top panel for now, the top three panels, the top row. This is showing you this event in this extreme event ratio. And I should just introduce the topic. We hear it very regularly in the media that the number of extreme events are increasing in terms of precipitation, and we might hear about a 1 in 100 year flood event or precipitation event or some other return period. And this we found leads to quite a bit of confusion with users. They think a 1 in 100 year event, well, if it happened last year, it's never going to happen again in my lifetime. It's going to be 21, 23 or 21, 24. And it's leading to a bit of confusion. So what we've thought about here is something very, very simple. So if I just ask you to look at the top left panel, this is the average annual maxima of daily precipitation. So over a reference period recommended by the WMO, 1991 to 2020, we've pulled out the daily maximum precipitation at all the grid points you see there. So we pull them out, the maximum in each year, we take the average, and you have this average annual maxima. So that's what you might expect based on the historical data. Then in the middle, that's the extreme event that I spoke about earlier. So you can see it affected Germany, parts of France, Belgium, also into the Netherlands. And then by dividing, so the middle column by the left column, you end up with this extreme event ratio, which will tell you how many times or how much more precipitation did you get than what you've seen in the past at your particular grid point. I mean, this could be done on any data set. This is on ERA 5, just because we have access to it readily. So for this particular event, in the top right now, this is an extreme event ratio, and this shows you that there were values of up to 3, I think it was just over 3, 3.5. In other words, that particular event, the rainfall was at least 3 times what you'd see in that past reference period. So it just gives you an idea, rather than talking about 1 in 25 years, 1 in 50 years, 1 in 100 years, and having the uncertainty associated with that. This is just a very simple technique to try and give you a context of what the event was like. But to talk to my audience and to make it more relevant to you here in Southern California, I would like to show you exactly the same, but this is now for Southern California, as you can see. So nicely in the bottom left, the Sierra Nevadas come out in terms of the average annual maxima. The transverse range come out as well, just to the north of here. On the 5th of February earlier this year, I'm not sure if anyone was here and remembers that particular event. I think there were a few fatalities, unfortunately. You can see this atmospheric river event. I presume it might have been flown in AR Recon. You can see the rainfall in the transverse range. It was a south to north atmospheric river. If we now put that into this extreme event ratio on the right-hand side, there were values of about 1.5. I think it was just over 1.5. So in terms of that event, for one particular day, so you could do a longer period, but this is for one particular day on the 5th of February, the rainfall was 1.5 times what you would expect to see in that reference period. So it's just to try and convey the extreme nature of the event. So I hope that it's very new. I hope it's of interest and relevance to you. So that's the end of the first half. There's no interval. I'm going to carry on because I know we're pressed for time. So what I want to do now, this is where Dwayne and I first met a long time ago now, in terms of atmospheric rivers. So down at Scripps Oceanography, Marty Ralph and the Center for Western Weather and Water Extremes have developed a program called Atmospheric River Reconnaissance, which is growing and growing, and I hope I'll give you a feeling of how that's growing as these slides go on. And what they're trying to do is observe atmospheric rivers better, and I'll tell you exactly what they are in a moment. Try to observe them better, to improve the forecast, to help water management and flood preparedness in the western United States. You might then ask, well, why are you from 5,500 miles away interested in something that's happening here? Any more observations that can come into our system, into the global system, that is, into the American GFS model, the naval model, European centers model, will help. So any way we can help to try and promote observation gathering will help our initial conditions and improve the forecast. And anything that improves here potentially will improve downstream, 5,500 miles away. And there's another reason, and we'll come on to that, and that's forecast diagnostics, and that's why we're very much interested. So just to take you through, what is an atmospheric river? It's basically an area of intense moisture flux, water vapor flux in the lower atmosphere. Left-hand panel is showing you a traditional synoptic map. So we have the warm front on the right-hand side, the cold front, trailing cold front, and that red and orange region, this is the atmospheric river, where you have a low-level jet, high moisture content, and it's when these features, which you can see they're very low level. In the right-hand plot on this screen, this red area here, this is the AR. When this coincides with, it could be a mountain chain or it has some other dynamical uplift, you can get extreme events. So atmospheric river reconnaissance, I've just mentioned briefly what we're doing, why we're interested in it. So atmospheric rivers are important for extreme rainfall. You saw that on the slide one ago. And predictability, of course. So if you get the atmospheric rivers better constrained, it might help with the predictability in the forecast system. Why are we involved from this far distance? Why are we interested? To improve understanding and NWP, numerical weather prediction. In terms of Marty's group, CW3, so Marty Ralph, Dr. Marty Ralph at Scripps, for water resources management and flood preparedness, all of the extra observations that go in from dropsondes, radiosondes, ocean buoys, the temperature, humidities, and winds, and surface pressure, all go into our systems, and then it will allow us to, as I say, number one, improve the initial condition of the forecast, but then also potentially identify model issues. We call them intensive observing periods, so these different flights, these go back a few years now, to 5-6 years ago. These were particular IOPs in 2018 on the left, so these are 5 particular IOPs with multiple aircraft. On the right-hand side, we have 2019, so different IOPs, obviously, with multiple aircraft. And most of these, so the black dots that we see on the screen, we just focus here in the top left-hand panel. So on the 27th of January 2018, the warm colors, so the oranges, the yellows, the reds, this is the water vapor flux, and the black dots, these are the dropsondes. So mostly the dropsondes are trying to target the atmospheric river, the water vapor flux. And this is done largely based on looking at precipitation impacts across the western United States and seeing where, if you improve the initial condition, or where is the ensemble most sensitive to extra observations, and then potentially you can improve the forecast, which we're working on now in terms of assessing those impacts. The ocean buoys, in fact, this is the last time I saw you, Dwayne, I think, before today. This was at the AMS in 2020. So there was that's total chance. So this was, in fact, let me just back up one moment and just explain what we see here. So part of my work as a forecast analyst, just to go through this, and let me just ask you to look at the right-hand side. This is a data coverage chart from the European Centre. But if you just look at this zoomed-in plot on the right-hand side, this goes back 4.5 years ago. There aren't that many observations out there. Prior to AR Recon deploying more, or making it possible to deploy more buoys with pressure sensors, it was pretty data sparse upstream of the US and North America in general. This line that is very nicely captured from LA down to Hawaii, this straight line of purple dots, this is a deployment of ocean buoys from a ship of opportunity. And these came in, I remember being sat at, in the AMS, the American Met Society annual meeting in Boston. It was very exciting to see this actually come to pass, as you can see there. And then if we just move through, this is now last year, 2023, different colored dots, but thanks to AR Recon, they obviously drift around with the currents, but we're now really plugging in more of these gaps. So we're filling in the gaps across the eastern and northeastern Pacific, which is tremendous to see. As we then move forward to this season, so this has grown and grown and grown. What this is showing you, these are on the 1st of November last year, 2023, so similar plot to what you've just seen. But this is the ocean drifters, the buoys which are reporting pressure, which we see in the global telecommunication system. So that's the system that transfers all the observations, and we then use those in the forecast system. So that's what it was on the 1st of November. If we go to the 1st of December, there were 2 US Air Force flights, which you can see to the south of the Aleutian Islands. So they launched and dropped buoys into this data sparse area, especially where the Aleutian Low is, to try and capture that better. There was also a cruise out of Southern California, and you can see those in the bottom right here. We then go forward to the 15th of January this year, and this is, I have to say, very exciting to see. So in terms of another data sparse area, these were 2 flights out of Guam. so north of Guam, southeast of Japan. So we now have blue dots, and there are multiple buoys in here. We're now up to 57 that are reporting, and then we go to the 1st of January. You can start to see them even in 15 days spreading out. And I just asked you to focus just off of the Pacific Northwest. This was the last deployment of the year. It was over 80 that went out. I saw 73 in this particular window. You can see a cruise going out into the Aleutian Low region. So thanks to AR Recon, and I really stress this, we are filling in gaps in the global observing system, which is absolutely tremendous in terms of capturing the initial condition across a pretty data sparse area. Not in terms of satellites, that's well covered, but in terms of in situ, and the pressure observations we get really are fundamentally important. So I just wanted to share that with you, and how exciting it is to see it come to pass with all the colleagues there at Scripps. So just to go through the latest season, this wasn't all the dropsondes that were launched, but just wanted to show you what we see from them in terms of our regular monitoring. So I think this was roughly 1,000, I think it was, or roughly 900 to 1,000 drops. The red ones, I call them high resolution ones. These are the buffer data. We get very high resolution data that's sent to us, so much more data goes in to our system. The blue ones, these are mostly from the US Air Force, so currently they're lower resolution, but still important all the same.
And you mean vertical resolution?
Vertical, yeah, vertical. Sorry, Dwayne, yeah, vertical. I'm not sure if this is, I think we might have frozen. But just to speak to that, Dwayne, yes, it was vertical resolution. Oh, there we are. Thank you very much. Yeah, just to say vertical resolution. And just to add a few numbers onto that, so if we're looking at the buffer, so the high resolution from the NOAA G4, you're looking at, say, 200 to 250 pressure levels that are assimilated, which is roughly 2 to 3 per model level across that profile. The US Air Force can be between 15 and 40, so it's about a fifth. It's partly to do with the communication problems, but that is or communication limitation rather than problem. So with all of that data, just to show you a few things that we see. If we start on the right-hand side, this is the specific humidity. The black, this is our first guess, or the background, so this is a short-range forecast, 3 to 15-hour lead time. What we find is quite an issue in terms of the random error, the standard deviation of the error. Was above the boundary layer, about 800 millibars, 850 millibars. You can see this little black dashed line here. So you end up with a random error of about 1.2 grams per kilogram. These are 20 hectopascal layers. It's obviously much lower. It's corrected by the time you assimilate the dropsondes. So this is now, so you go from the black line to the red line. The other point to pull out here, so what I'll say before I just move on, this is a problem with placing moisture in the vertical. So satellites can give us a good representation of the total column water vapor, but it can be difficult to get that right in the vertical, which is what we're partly seeing there. The other issue, if you look at the right-hand panel again, it's a little too dry in the boundary layer. So this is the mean error, mean background minus observation in black, and then the mean analysis minus observation. So that's after all of the observations have gone in, and it's a little too dry in that boundary layer. The other thing just for here, and I'll say two more things on this here. Middle plot, just looking at the temperature. This issue with the temperature is related to the specific humidity problem. So there's a random error of about 1 Kelvin in the temperature. You see a cold bias in the model as well, so the model is too cold. And then lastly, which is going to dovetail very nicely onto the next part of this presentation and the final part, if we look at the winds as we go up, we see that the jet stream winds, the upper level winds, they tend to be too weak within our model system, and we'll come back to that. So this is what we see at the dropsonde profiles. We'll come back to that now, as I said. When I mentioned earlier on introducing AR Recon, We're obviously interested in initial conditions, improving the estimate of the atmosphere to give us a better forecast. But it really can't be underestimated how important they can be for diagnostic studies. So this was a little study that I did with colleagues, Ryan Thorne, Chris Davis, Marty, and two colleagues, David Richardson and Florian Pappenberger at ECMWF. This was using all dropsondes from 3 different seasons, so 2020, 2021, and 2022. So if I can ask you to look at the top left-hand plot, this is showing you everything that went out there in those 3 seasons. And in particular, what we then did, and I'll move on to that slide there, but what we will do is use different transects. So there were many different IOPs. Some of them, by chance, would be a little unfair. They crossed the jet at near right angles, or it was perpendicular, to the jet, which meant we could have a look at the structure of the jet stream. And there are hardly any data sets out there where we could do it. And I remember being on some forecast calls and just asking, could you just tweak this a little bit? I think this is going to be a cracking case study. And they really came out quite beautifully. So we used 21 different transects, and that will be on the next slide. In the interest of time, I'm just going to tell you very briefly what you're looking at. On the right-hand side, this is a scatter plot of the observed winds from dropsondes against the model. This is the background, so we're looking at 3 to 15 hours, very short range. Most importantly, if we just focus on the red area, so this red band from the left down to the bottom right, this is what we've signified as jet stream winds, so winds greater than 50 meters per second. And it's at these high wind speeds where we tend to see that the model doesn't quite capture them. And we've plotted the QQ points on there. So if we look at the 99th percentile, it's below that 1-to-1 line. So there's a signature here that, and in fact you can see it in the bottom right, it's roughly about 1 meter per second. So the jet stream is roughly 1 meter per second weaker, so there's a slow jet bias in the model compared to the observations. But if we just look at these, these jet stream transects, and let's focus now on the right-hand side. So what this is now looking at those 21 transects that have cut the jet in a perpendicular fashion. These are all from the NOAA G4 aircraft, so we're flying at about 150 millibars, 43,000 feet, and it gives us a lovely transect right the way across the jet. So this right-hand plot, three columns. The left-hand column, this is the wind speed, temperature in the middle, potential vorticity on the right. So this is looking at the structure of the atmosphere. From top to bottom, analysis at the top. So this is after you've seen all the observations, so they've all gone into the model. The second row, this is the background, so our short-range forecast. Then on forecast day 2 and forecast day 4 at the bottom. And this is just in the high resolution, the deterministic forecast in those particular years. So the main points to pull out here goes back to what I mentioned about the slow jet stream bias. So if we just look at the left-hand column of the right-hand plot and just look at this panel here, so the second row, left-hand panel, the jet stream is given by this middle blue region. This is actually this is really capturing this slow wind bias that I mentioned to you. There's a significant slow jet bias in that region. We don't see it as much on day 2, which might be a sampling issue. We do see it again on day 4. So there is a signature that the jet isn't strong enough, which would then have implications for the transit of extratropical cyclones, development along the jet, and then predictability. Temperature's given in the middle, but in the interest of time, I'll just ask you to focus on the right-hand column. There's a dark black line, so this bold line, which is what they call the PV=2 contour, which is synonymous with the tropopause. So we're looking right at the top of the troposphere. And those black contours, and I should have said that about them all, these are the observed composites of these 21 transects that you see in that top left plot. But what you'll notice as we go from the top right, the potential vorticity in the analysis, to the background, to day 2, to day 4, there's this growing blue and then magenta area. And what this is telling us is that with forecast lead time, so as our forecast goes forward, the jet stream, the gradient basically across the jet is diffusing away. So it's sharp within the observations, but the model just can't keep that strong gradient. And you see it coming out very plainly. And I must say, it's these unique transects which have given us this insight that it's just not being captured well, which then has implications, as I say, in terms of predictability, downstream predictability, impacts in the near term on the west coast of the US. It could be the same in the Atlantic. So it's a pretty significant result. We've diagnosed it. What is it? That is under investigation. There are a couple of things we think that could be the issue here. One is the application of too strong I suppose, overturning in the model, which we're not handling well here. It also could be the model resolution. So in terms of, I think it's about 300 meters between model levels, which is not necessarily enough to capture the sharp gradient at the jet, especially as you go forward with lead time. And I think I'm basically bang up to the wire here. So I just want to present a few conclusions, and I hope it's been of interest to you. So firstly, the Copernicus Climate Change Service, the monitoring activities, it's quite a broad program at ECMWF in terms of monthly bulletins, annual summaries, European State of the Climate Report. Also web articles that come out from time to time when there's a particular interesting event that's going on. I must say there have been more and more events over the last year, so they've been more regular. And ERA 5, as I've spoken about quite a lot, is used heavily within our service. ERA 5 itself, you do have to be careful. It's a reanalysis. It's a proxy for an observation. It's more able to capture or discriminate precipitation in the extratropics. You have to be careful in the tropics. So there's more confidence in the extratropics. And I hope I've conveyed to you, AR Recon has been a growing and growing program. It is an absolute privilege to be a part of it with all these unique observations that are taken, benefiting colleagues, people in the Western United States, but also globally. It's given us the opportunity to improve the forecast, but to identify biases which we wouldn't necessarily be able to, especially in that upper troposphere, lower stratosphere region. There's a few references there if you're interested. But I'd just like to say it's been a pleasure to be here. I hope it's been of interest to you. I hope it's not been too tiring on a Friday afternoon. And I'd welcome any questions. Absolute pleasure to be here. Thank you.
Okay, so when have I put my sunglasses on? Who's the first one? The first one? Evan. Evan, can you unmute and ask your question?
I could, but there's a more interesting question I'd rather ask instead.
Okay, you can only ask one. So do the more interesting one.
Okay, so I'm not sure I have the terminology right, but if you look at the jet, there's helicity around the core of the jet. And you've talked about the fusion of winds out of the jet. Do you know anything about the helicity and whether that's larger than observed because of that diffusion?
Evan, that's a very good question. Did everyone hear that in the room? Do you want me to repeat that? No, everyone heard it. I don't. It's a great question about the helicity of the jet. I'm not quite sure, to be honest, but I'll be meeting colleagues who worked on this, so in particular Ryan Torn and Chris Davis. They'll be at the conference next week. I can certainly ask and come back to you, but I don't have a good answer at the moment. But thank you for the question.
And doesn't that go directly into precipitation in the sense that it produces updrafts?
You're talking about the jet itself now, sorry?
Yeah, the helicity associated with the jet.
Yeah, but it's in terms of disturbances along the jet, if you don't capture that correctly, then the interaction with and the development of extratropical cyclones won't necessarily be correct. Potentially the updrafts, as you said, in terms of potentially right exit or left exit, right entrance, I can't remember exactly now. I think that's correct. In terms of the updrafts, you are right, it will have impacts downstream on the precipitation. I should just say while we're talking on this, one of the point that's come up, which I didn't mention, please forgive me, is the moisture bias in the lower stratosphere in the IFS, so in the integrated forecasting system, which then has a radiative impact. So if you have too much moisture, there are then impacts on the radiation. So that's another aspect as well that could be an issue. But I can certainly ask colleagues next week and can always come back to you if that would help on that question. Sorry, I don't have a fuller answer to it.
Okay.
Thank you.
No problem, thank you.
Terry, can you unmute? I haven't got my reading glasses on, so there's no way I'm going to be able to read this question. So, Terry, can you unmute and ask your question? I can read the first three words in light of 5th February 2024. That's it. Terry. Terry's Cuba. Are you still on, Terry? Go down. We're going to scan for his presence. Yes, you're on. He's muted. Can you unmute him? Maybe you. What's this duck?
He's got her reading glasses.
I tell you what. If you can't, we'll take questions from inside in the room.
No problem.
As we're waiting for Terry.
Can she ask the question?
Huh?
Can she?
Oh, can.
Okay. In the light of the February 5th AR event that you were showing for SoCal in terms of the extreme event ratio, that they was in the midst of the multi-day heavy precipitation event locally, have you examined ERs on different time scale as well, especially ARs, 3-day and day events?
It's a great question.
Like, for example, I think I measured 4 or 5 inches of precipitation over 3 days at my house here.
4 or 5, wow.
Something crazy in that period.
Yeah.
And so I think that's a good question.
It's a great question, and it's something that we have considered. So I did have a look at different accumulation periods. So thanks for the question on the extreme event ratio. So I did look at different accumulation periods. That period seemed to be the most in terms of a daily accumulation. So this study was just trying to illustrate the method for one-day events. It is a great question. So it's just been submitted as a paper. Who knows how it will get on? Hopefully it will be well received. But this is one of the comments that we've made. You could extend it to 3-day accumulation. It could be 2-day. It can be whatever you want it to be. I would expect it to go up in terms of event ratio for a longer period, so whether it's 2, 3, 4, or 5 days. One thing to add, which I think we need to be careful of, and I didn't say it there, is ERA5 will be underestimating the precipitation. It should be, what we find is by looking at some of the extremes before, that bias, when you look at it in its own world, is taken care of, but we still have to be mindful that it might not have estimated the rainfall on that day particularly well, which probably, I think it was about 75 millimeters in ERA5, which would tie up roughly with what you're saying, but I imagine it was more in the mountains here. So no, great question, and it could be extended to other totals.
I have a question, a couple of questions, but I'll go to the audience first. Do you have one, Nathaniel? Okay, Nathaniel.
I wasn't sure, on your plots of those buoys, you talked about pressure. Was the pressure just a proxy for the other exciting measurements, or is it actually pressure that you're wanting from these things?
Surface pressure. So there are two main things. I mean, they're developing these buoys as well now. So there are two main things. One is sea surface temperature, which we don't currently use in the atmospheric model. It goes into the ocean reanalysis. But the surface pressure, mean sea level pressure, those are fundamental in terms of getting the large-scale circulation right.
There have in the past been concepts to make measurements of sea surface pressure using active microwaves. We got as far as an airborne instrument in the 1980s. And I think the concept was kind of put aside because the operation community at the time felt they needed temperature more, better temperature profiling. Yeah. But I mean, I think there are people with concepts ready to go to do active pressure measurements. If the time is right for that, maybe it's worth an Aussie study or something. Just to see what difference it would make.
Absolutely. Pressure over global oceans. I mean, did I have the global
I
map?
forgot about that.
It's an issue of accuracy and precision as well, right?
Yeah. I think they were able to get. Yes. Okay. I think getting much better than 1 millibar is tough. If that's your kind of requirement,
yes,
then.
I think these are about. I'd have to check. I think it's 0.4 millibars. I think. but I couldn't
okay,
do
it's probably like
better
1
than that.
millibar over a 10-kilometre kind of.
Actually, a little bit of historical context. The precursor to OCO, which tries to measure column carbon dioxide, the precursor of that was measuring oxygen exactly for the purpose of trying to estimate surface pressure to below a millibar. And the conclusion was it can be done, it can be achieved by measuring oxygen content in the atmosphere with the oxygen at the oxygen A band, but you have to have very high spectral resolution to account for all those unwanted effects that can distort the bias retrieval above a millibar, like thin aerosol and all that kind of stuff.
And it would only-
that then mapped into OCO and became the OCO kind of approach, but the early work was done in the 90s on oxygen, specifically for, but of course, in that circumstance, it's not all weather.
Yeah, it's clear. It's also
clear
needs,
sky.
it needs clear sky.
Yeah,
Whereas
it's clear
the
sky.
microwave could do not so great in precip, but could certainly do in clouds, as I understand it.
But I guess the drive, the push for surface pressure measurements remotely, globally, sort of went away. Yeah, I guess, right?
Remember, Ziad was pushing on that pretty well. and
Yeah,
I thought it was-
no, I'm talking about the community.
pull, I think the pull went
know,
away. The push was there. The pull, there was not.
The pull went away. Yeah, that's what I mean. I don't mean people working in the weeds doing this. The community who would use this, that pull, kind of disappeared. But anyway, so it'd be interesting if that comes back again.
I mean, it's one thing to
because it
have
opens up a new.
an arbitrary buoy have a certain, accuracy. And then to say that the remote sensing is 3 times worse, so is it useful? But you have a whole ground track, but then you have a gradient
Yeah, but
across the
it's
storm.
exactly the same questions that came up with OCO and the flask data, more accurate than the OCO, but having the volume of data and the spatial context of that data trumped it. So it's exactly the same. It's the same story, just slightly cast in a different way. But anyway, that's a little bit of history. I think we have one. I've got a question for you, but
sure.
one more from Brian's got his hand up. So since I know Brian, I'm willing to let him jump the queue and ask the question. Brian,
I'm glad that you don't have to read my voice, Graham. So,
thank God for that. Yes.
I just following on the Atmospheric River, the event that we had this year, it was really strong, but it was actually quite confined to the coast. Parts of West LA around UCLA had over 20 inches during that time period. There was quite a lot in the San Gabriel foothills, but it actually petered out in the mountains. The rainfall anomalies for the season weren't that excessive in the mountains, whereas the previous year, it was much more focused on the San Gabriel range. So I'm kind of curious, have you looked at the diversity of atmospheric rivers and maybe how deep or shallow or, really where is the amount of forcing strongest? Is it inland or is it there a shallow feature near the coastline? Can Era 5 handle that sort of subtlety? I'm really curious about that.
It's a very good question. Are you thinking of this event in particular or more general?
More general, but this event is an example of an event that was really strong right along the coast, not so much in the inland valleys. Well, it was less so in the inland valleys, whereas the previous year it was more focused in the inland valleys.
Yeah.
It was also forecast bust in the mountains. They said it was going to rain a lot, and it didn't.
Yeah.
Okay.
Yeah. It's really interesting. I'm just kind of curious about what may have caused that difference and whether models would pick up on it.
I don't know this case in particular, other than studied it here, and particularly the fatalities around it. I think there were 3 fatalities. There'll be 2 major ways to get moisture out of the atmosphere. So think of it, the atmospheric river is largely a horizontal flux. So you either have a dynamical forcing, which could be the cold front in particular, it could be convection along that cold front, or the other one will be the mountain chain. So it hits the mountain chain, perpendicular in particular will be the most efficient rain out. Those will be the 2 ways to get the moisture out of the atmospheric river. In terms of Have I looked at different ones? I haven't, to be honest. I've studied atmospheric rivers, forecasting of them, but why some do and some don't is a very good question. They have spoken about aerosols being an important feature. The other one in terms of what back in Europe is called a forecast bust, here will be a forecast dropout. I think same thing, same feature we're talking about. So they talk about mesoscale frontal waves. So these are little waves that run up the cold front, which can lead to very large uncertainties in terms of landfall. So it could be, in terms of predictability, could be to do with a feature like that. I'm not sure, does that answer some of your questions there?
Yeah, I mean, it could be small scale bands and structure and how they interact with topography. You know, some of them maybe respond more to shallow topography versus deeper topography. I think there's a lot of interesting submesoscale features that are in these atmospheric rivers that would be fascinating to study.
Absolutely. No, I agree with you. Thank you for the question.
I'm getting relegated towards the end, to the end. But anyway, okay, now you go.
Very quick point. If you show again the dropsondes biases, the background. Yeah, that's the previous one. If you look at the moisture, it really does seem to show that the background has a boundary layer that is too deep compared to the sondes, right? Because you see that sort of dipole of too much moisture above the boundary layer and too little moisture below. Yes. And so it does seem to be that the boundary layer is a bit too deep in the model rather than in the observation. So that may be that
could be one
hint for something on the physics.
We need to focus on the PBL, don't we? Okay, two questions. One's really kind of just a procedural one. Your rain gauge data, did you create that as your own database? Well, I guess my question is, did UX spend a lot of time, energy, and effort over the years to pull together the global rain gauge data and homogenize it, right? I think it's called GPCC, and that feeds the GPCP project, right?
Yes.
So there's quite some effort to homogenize the data, because not all rain gauges are equal, and not all rain gauges, the quality of them are equal. So there's quite some effort gone into that. So your rain gauge data, did you guys create that at ECMWF as your own, or is it something quite...
No, so they're all from synoptic stations.
Yeah.
So they all come in on the GTS, and then...
But there's been no
No.
Quality QCing of them?
No, there's only one QC that I've done. I removed anything greater than 500.
Right.
Which you do lose a few events. You could lose a few tropical cyclones. But what I was finding, there were some stations that were reporting, it was 999s, 999.2. So there were a few issues. So I just thought, no, let's just get rid of it. Obviously, no negative numbers, but that was it.
Right.
Internally in the archive, so some of them, they'll come in as 6-hour chunks, and then they're put into a 24-hour total.
Right.
But they all come from the synoptic network.
Okay, so at some point when you start to use these data and promote these data, you're going to have to kind of contrast it against those other rain gauge data sets that have been kind of worked and studied and sweat over a lot. So you probably have to do that at some point. My main question is more intellectual, philosophical. I think we're at a kind of intellectual kind of block at the moment in terms of severe hydrological events and predicting them. Mm-hmm. So here's my concern. It's a concern, and I don't have an answer, but my basic question to you that I want to answer from you has to do with the evolution of the IFS and where it's going, particularly with respect to resolution, because as you know, resolution's really an important issue as it represents convection and the heavy precipitation from convection. Mm. And it looks to me, from things I've seen from the diamond and all of the K-scale modelling and so on and so forth, that the models aren't anywhere near converging with respect to severe rain from convection. There's no convergence. The higher the resolution, the more intense is the rain. And we don't know where the real answer is, but it doesn't look like there's model convergence. So that's, to me, raises a really serious philosophical question about are these models fit for that purpose? And are the forecast systems in turn based on those models fit for that purpose? However, having said that, I would think that there are certain, not all raining clouds are the same. And so I would think that there are certain types of rain phenomena that are better represented by the models than others, like obviously severe convection and so forth, with a lack of resolution convection, not getting updrafts, and the stronger the updraft, the more intense the rain. If you don't have that strong updraft, how can you make the intense rain? But there's other rain that you probably are, the dynamics you are resolving, that would shape that rain. And so I think we should think about not just rain as a whole. Your map there, you do a better job in the middle and higher latitudes, and you do a crappy job in the tropics. We ought to be thinking about these more phenomenologically in terms of the kinds of dynamics of the rain systems that underpin this, and start to break it down that way. Because, you know, you obviously have some skill with respect to precipitation, but not everywhere. We want to understand where things break. And I think it's the resolution and the lack of dynamics. Because basically, air has to be lifted to make air rain. And if you don't lift it right, you don't make the rain right. It's as simple as that. But certain circumstances, when you've got slantwise convection, you've got large scale, and you're resolving that, like in the mid-latitudes, you probably are capturing that. So I would think we ought to be thinking about that a little bit more in terms of phenomenological, breaking this down, classifying raining systems a little more sharply than we do. But philosophically, I just don't see the models really are fit for purpose in terms of making projections about changing of the severity of weather, particularly as it relates to precipitation, when we know we're missing basic processes that make the rain. So I guess but my question is, and I know IFS has done experimental forecasts out at 0.9 kilometres. Yes. I think it's 0.9 kilometres.
It's 9 kilometres.
No, you're 9 kilometres, but they've done down to 1 kilometre, 1.1 or less than 1 kilometre. They've done some experimental forecasts out. I know they've done that. What's the thinking at the centre about where the model is evolving to in terms of resolution? I know there was this artificial barrier, you could not go down below 5 kilometres because that becomes now a regional model, and you got all your little blue states that have to do their regional stuff, and that was an artificial barrier. But I think that kind of went away. But so, what's the direction of what's the thinking in terms of the IFS and its evolution in this coming decade? From now to the end of this decade. So, do we expect to see it always at 9 kilometres, or is it going to get 5 kilometres or 1 kilometre, or what's going to happen?
It's a very good question. I'm not sure on the whole strategy. They're putting together a new plan now. I think there are probably two or three things just to talk to immediately. So at the moment it's at 9 kilometres. There's the old high resolution, which is still there, but there's the ensemble system at 9 kilometres. I think the first topic to raise is that ECMWF is running Destination Earth. So they are testing...
That's kilometres, right?
Yeah, I think it's... You'll have to forgive me, I might have this wrong. I think that you see it regularly. So as a forecast analyst, you might see things that we put in, or the centre will see things. It's either 4.8, I'm sure there's a 2.8 or 2.4 kilometre. So they're assessing them to see how they do in terms of extreme events, convection, extratropical cyclones and things. In terms of where we're going, higher resolution, I'm sure will be coming in terms of the ensemble. What that will get to, I don't know, but I'm sure it will go there.
It's almost inevitable.
I think it's inevitable, and the Destination Earth is feeding into that. But I say it's inevitable, and then I'll go to another line of thinking, and that's the artificial intelligence machine learning models. So at the moment we're running, I think there are 3 or 4 at the centre. So there's the AIFS, Artificial Intelligence Integrated Forecasting System. There's GraphCast, there's the Google one, there's Pangu Weather, and there's another one, I forget all the different ones. What we're finding is that the AIFS, amongst the others, they're trained on ERA 5, so they're at a 25-kilometre grid, and you can tell the difference between the IFS and the AIFS. You can just see one is smoother. But in terms of skill, it's right up there with the IFS, or it beats it, and it's a bit more consistent. So to answer or to put a thought out there, that I think the progress over the last 3 years has been immense in terms of machine learning. I don't know where that's going to go, but I imagine that will have a bit of a bearing on some of the questions you asked. But you've got to train. Well, see, it's a great question. This is an interesting one because there was an event, I think it was in Dubai. It was in March, early March, and it was flooded. I think the airport was closed, which caused a huge issue out there. And I was talking to colleagues about this. Well, we've not seen this event for a long, long time, and the AIFS did pick it up.
I picked it up.
And you were there, were you?
No, you said the AI.
AIFS. To the artificial intelligence, that picked it up well in terms of the precipitation. Didn't get the magnitudes right, but it did have the pattern right. But in terms of artificial intelligence models, there is which I think gets to your question as well, the skill is up there with the best NWP, but it doesn't always get the processes right. So you actually look at the features themselves, and they are, looking at cold fronts, they're smoothed out, they're not as precise and defined, which of course will have an impact on the precipitation. So that doesn't really answer your question. It's more putting more ideas out there.
We don't have an answer.
We don't.
Because we're all in this boat together.
We're all in this boat together.
Which way it's going.
Yeah, and it's.
But I'm glad, Graham, that you asked that question, because the question about is it fit for purpose, and the answer is probably no. Those global cloud resolving models are trying to create updrafts at scales of 2-3 kilometers. Those are not the real updrafts.
What I think we can say is the climate scale models, the CMIP class models, are definitely not fit for purpose for this problem of extreme weather, right?
Well, I don't know if that's true. I don't know if that's true, because they can develop ways of representing convection that, from a climatological perspective, and often from extremes when they look at them, they are better than
so you think the CMIP models can project extremes better?
Global cloud resolving models?
Hydrological extremes better? I'm not talking about...
Because none of them is resolving them. None of them is resolving. One of them, there's generations of people have worked on them, and the other one is no, just a few years.
Yeah, I don't buy that. I don't buy CMIP. Can it come anywhere close to it?
I don't buy the global cloud resolving models at all. So.
I'm not. Who says global cloud resolving model? All I'm saying is that you have to restart resolving that process. Global cloud resolving models aren't necessarily resolving that process either. But there's no way that CMIP models. If you look at the precip, the most extreme precip, the 99% of precip from the models, CMIP models, the diamond models, and then other models, then you've got the NICAM models even down to 400 metres or something. If you look at it systematically, the maximum precip out of the climate models is an order of magnitude, not 10%, 5%, an order of magnitude smaller. The heaviest rains are an order of magnitude smaller than the heaviest rains from the higher resolution models. And it'll be an order of magnitude lighter than the heaviest rains out of your model. So there's no way that they can do
I'm not saying the CMIP models are better, I'm saying they can be made better.
Well, I'm just saying that they're not fit for purpose either.
Huh?
There's room for them to be made.
Yeah, because they can rely on parameterizations of deep convection that don't exist right now, but that could potentially...
Well, I'm old-fashioned. I think if you've got a tool to do science, that tool has to resolve that which you want to do science about. If it doesn't resolve it, it ain't a tool to do the science. So if your science is about extreme range in a warming world, and your tool doesn't resolve any of the stuff that makes that extreme rain in a warming world, it's not fit for purpose.
Graham, we don't run hyperspectral forward models online on the CMIP models. We don't. But we still trust a lot of the radiation.
That has
right?
nothing to do with it.
You just said if it doesn't resolve it, I don't trust it.
No, I'm saying
Right?
the process of heavy rain, if you don't resolve the process of heavy rain, how can you use that model to make projections about change in heavy rains if it doesn't resolve it? It's got nothing to do with spectral resolution of
I'm saying
That
when you model radiation, you aren't actually modeling it at the fine scale of,
But you don't necessarily have to.
Right, well, that's
But
what...
I don't
You've got the
think
total energetics of the system is what you're trying to model. You don't have to necessarily do it at 1 in per centimetre. But you do have to model heavy rain if you're making projections about change in heavy rain. That's my point.
But then you have to wait for models that have 100-meter resolution.
I'm not saying we don't know. We don't know. But what I can say is 60-kilometre models don't have the resolution of the processes that make heavy rain. So you can't make scientific projections about changes in heavy rain with a tool that doesn't see it.
But Graham,
I mean,
I
it's
don't
as
want to.
simple as that.
I don't want
I
to
don't
continue
know what
on
I'm
this.
missing.
But turbulence. I mean, there's a lot of research on turbulence, right?
Sure.
Right. And we don't need to know how the air flows around a tree
No.
exactly in detail to know what the 10-meter wind is going to
Yeah,
be,
but-
right?
but
It's kind of the
you're
same
missing
thing.
the
But let's
point.
not belabor on this.
Yeah, no, we're missing the point. Yeah, you're totally missing the point. You're completely missing the point.
I think CMAS model. I find CMAS model resolution is low to resolve the extreme. That's it. Okay.
Anyway.
No. I mean, it's a really interesting comment, and
Well,
honestly, it is. No, I'm just being polite. It is, because this question comes up regularly about, which is part of the reason in this piece of work about extremes. We hear it all the time. The extremes are getting more common or more frequent, and you start having a look at the data sets, and I don't necessarily see that. And in terms of ERA 5, so ERA 5, you've got to be careful of it. And tropics, there are questionable trends there. I mean, this is moving on slightly from that question, but it's answering another question in terms of, you hear it regularly, but where's the evidence? You need to have the evidence to prove what you're seeing. I mean, that then comes on to another question that Dwayne and I mentioned earlier, I think, about defining an event, making sure they're independent events. Are they independent in space, in time? But I think there's more work to be done there. That was it's a slightly a side question from that discussion you just had there, but it's all related in some respect, I think.
So even the models have an adequate resolution to resolve the river. I mean, you're resolving
Yeah.
the bulk transport
Absolutely.
carried by the rivers, right?
Definitely.
How it rains along the mountain range, that's another question.
That's another question. And
But you're getting I would think you're getting the bulk of the water transport more or less resolved right in these rivers.
yes, there will be errors within it, because I forget now, someone mentioned about where the moisture is. Did you mention the moisture, or someone online, I think, about having the moisture in the right place, whether it's in the vertical or spatially. But I'll give you an example. You're getting it roughly right, because if we go back to the AR Recon, the planning is based on forecasts. So the model is getting it good enough that you can plan your forecast 48, 72 hours ahead. It's there even more than that. But I think that question, if we go to the seasonal timescales, you've looked at before, Dwayne, you're looking at maybe the numbers across the basin. If you're looking at the late medium range, you're saying, well, is there going to be an event here or there? When you get to those timescales, is it one river basin in the transverse range versus another? The question becomes more precise as you get down, obviously. But the bulk, yes, I think. But then where it is in the vertical, what the structure is of it across, that's where those questions become more important, which is partly where AR Recon is coming at.
But this is well over time now. But
Sorry,
are you guys
sorry.
looking forward to EarthCare and the vertical Doppler information from EarthCare?
I believe they are. I don't know a huge amount about that,
Okay.
Dwayne, but
Okay, just
I'm
curious.
sure they are. I'm sure they will be nice. Good.
We should call this.
I'm sorry. I'm sorry it's overrun, but I hope so. Sorry about that.
It's good. That's
Good.
a good indication.
Wonderful. Thank you again, everyone. Thank you.